Okay, good morning, everyone. Okay, so today I'm going to talk about some UQ applications and start with some theories on how to apply UQ in complex Earth system modeling. Original plan, I was going to talk about how we really implement some scalable calibration techniques in a complex system. But later on, after the discussions with you and after listening to the several talks in the previous days, I will try to focus more on some simple, maybe trivial concepts, but maybe it's of your interest in applying those in complex Earth system modeling. The second half is still on calibration, on how to actually enable those techniques for the computationally very demanding Earth system. So I will not talk a lot about the details, as Chris and others has explained very well, of all the different sources of uncertainty to be quantified. So we have a really complex Earth system model, or climate model. It is multi-phase, multi-component, and involves multi-discipline processes at multiple spatial and temporal scales. And we have such a high-dimensional parameter space, and so we don't have adequate knowledge about all the processes and the parameters, and there are existing spatial temporal variability and heterogeneity. So temporal we call variability, spatially we call heterogeneity normally, and we have resolution and scaling issues. To me, I agree with this sort of classification system of how we describe different type of uncertainties. The first one is monostructural uncertainty, which we have talked a little during the first several days. That include the model inadequacy because of the assumptions, simplifications, approximations due to a lack of knowledge of the actual phenomena, and there's also lack of knowledge about initial and boundary conditions. Someone may argue this doesn't belong to monostructural uncertainty, but this is arguable. And then parametric uncertainty. This is something we talked yesterday. This includes uncertainty related to parameterization, how you add the different modules to describe system, and also how you introduce parameters. And next, how you assign the parameter values. So these are all parametric uncertainty. This is because you don't have enough prior knowledge about the parameters, values. You don't have measurements, or you have measurement errors, could be large or small, or you have under or down sampling. You have only really low resolution data, and you want to go to a high resolution information. And also, if you do have calibration practice, but still it can be an ill-posed problem, such that the parameters cannot be uniquely determined, or you have inaccurate calibration because of your technique is not applicable. And this is a famous term called the right answer for wrong reason. If you have two modules and you adjust the parameter values, it could be that your two modules are totally off, but by manipulating the parameters within the two, you are able to get a good match. That's the right answer. You could have good match, but you have a totally wrong reason. The third uncertainty category is the data forcing uncertainty. This could be from the instrumental errors or data consistency. You have different instruments or different people in charge of data collection, or there are data gaps, resolution, and scaling issues at different temporal spatial scales. And the last one is the natural uncertainty, which we have no control. That is including variability and heterogeneity. This one is more about how we describe this variability and heterogeneity. In reality, it is just simply impossible to collect data or get enough information for all the parameters, attributes at any spatial grids or at any temporal time steps. So we have to use some descriptive approaches to describe the variability and heterogeneity. They are natural, but you have to describe it very well. Okay, first exercise, without just giving a without talking all the time, let's have a little break, 30-second break. So a simple question, how likely is it that the spinner, this is a Wheel of Fortune game, the spinner will land on a blue space? I hope you have no trouble differentiating blue and other colors. And someone may have trouble differentiating green and red, but this problem is irrelevant. So, okay, so you have now 20 seconds to give me an answer.
Problem. Because we're going to adjust it. Yes.
It's too loud?
It just has too much. Just speak loudly for now.
Okay.
We're going to check it out.
Yeah, I'm fine with that. Okay, 10 seconds.
It's like less than 50%.
Okay, so you make your own judgment, or you're defining your own descriptive system. So any answer is fine. So don't worry, you don't lose points or something. Yeah, I will try to do a survey. Hello, thank you. It's very nice. Oh, you can discuss with each other.
It depends on what's the defining of certain. So, for example, for the IPCC,
Yes.
They will say that certain as a qualitative term. So when they say virtual certain, it means more than 99%.
Thank you for the discussion. This is actually what I want to see. So it's really depends on how we define a system. What is certain? What is probable? What is unlikely? What is impossible? So just choose the one that you believe is more reasonable. So I'm not against any of them. But okay, now we're ready to do this survey. So how many of you are thinking the probability? I don't want to use the probability yet. So how likely is that the spinner will land on blue? How many of you choose certain? No, of course. How many choose probable? Okay, I'm expecting some answers. Okay, about 12, 13. How many unlikely? 3, 4, 4.5? Okay, impossible. Of course, that's not an answer. Okay, so we are focusing on probable and unlikely. So actually this question is, I borrowed from my sister's elementary mathematical exercise book. It's for the second grader. They just want to give them a basic sense of probability and statistics. The correct answer is C, unlikely.
Oh my God.
Yeah. Because
So this is the American way to define it. So you're fine. Okay.
Damning so early.
Okay, so there are 12 blocks. Let's assume no other tricky stuff. So we don't play any, like we hang this thing vertically, and then this spinner is very heavy, and due to gravity effects, it's actually always pointing down. So forget about those stuff. Just assume we have equal probability of landing on any block. Then there are 12 blocks, and we have 5 below. So 5 out of 12, less than 50%. So in American way, we define certain as 100% probability. So for sure, impossible, 0 probability. 0, and just simply impossible. Probable means more than 50% chance. Unlikely means less than 50% chance. So this is the system we use. But again, I'm fine with how you define probable. To me, it is probable. 5 out of 12, 40% or something is probable to me. So again, so I think both answers are fine. Again, you understand now, the people from the whole world don't agree on this kind of descriptive statistics. So that's why we need to quantify the uncertainties.
How do you distinguish between possible and probable?
Possible is not used in this system. But yeah, I would say possible probably includes probable. Possible means probable and likely. So with some chance, maybe that's a possible. way to explain it. Okay, so this is the way that probably the whole world will agree on. So I believe we need to have a standard or a common way and a quantitative way to describe those kind of uncertainties. So this is, I would say, the best description. Cannot be even more than that. So we'll define a probability mass function for this discrete variable. I don't want to explain more on what is discrete variable, random variable, or a continuous random variable. I hope you have some idea about it as a basic introductory statistics. So for discrete random variables, we take only the discrete values. We use the probability mass function to describe its behavior. So let's define the color that the spinner will land on as a random variable. And for that random variable to be red, it's 3 out of 12 for the probability. For yellow, for green, for blue, we use these 4 numbers to exactly describe what's going on. So that's the way the whole world will agree on. That's the uncertain quantification to me. Another case is a continuous random variable. In this case, I was asking to give them suggestions on which site is a potential site for building a new wind farm for wind power generation, given the historical distribution of the hourly average wind speed. So we want the wind speed to be very high, averagely. And also, there's always some uncertainty related to or variability, you can call that. So which site is more ideal? In other words, which site is better to be a future wind farm if you have to choose one? Again, 30 seconds for this. See what's your judgment and what's your basic arguments or logic in there. Oh, I'm blocking this one. Okay, so selection of wind farms from one of the 4 sites given hourly average wind speeds. So I'll give you one hint is the average speed for the 4 sites are the same. So this one cannot be the judgment question.
Would there be a maximum speed over which the wind farm couldn't operate?
Yeah. Thank you for the clarification. So we want a wind farm that is more operable. So reduce the operational costs. Bottom right. Bottom left.
Upper right.
Okay, so
Upper right.
upper right. Okay. So
That's
no one choose the top left. Okay, it's time to. Okay, okay. You have 5 seconds to change your mind, and then we'll do a survey. That's the way I like. I always like to do surveys.
We need more information. What is the power curve versus the wind speed?
Yeah, exactly. Is it linear?
So let's say they are linear. They have a linear relationship. So if you have a low value of wind speed, low wind generation, if you have a tailed distribution, you have a tailed wind generation also. So the higher wind speeds, the higher wind generation. But averagely, they got the same average wind speed, so they got the same average wind generation.
But it's a cubic of the wind speed. It's not just the linear.
Yeah, it's cubic, but that won't change the shape a lot. So assume they have a monotonic relationship. A higher wind speed, the higher. And see, even if it's cubic, it won't change the shape of the wind generation. Or you can look at it this way. Let's assume these are the potential after we do the power system model. These are actually the wind generation. So let's treat the number 12 as the average wind generation. So then.
Second information we need is under what kind of extreme condition very large wind speed is then have to stop working because it's damages it.
So that will challenge the wind storage, like batteries for the energy storage. Yes, a very high wind speed will generate extra energy that we cannot use. For example, the higher tail here will generate too much energy that we cannot use and cannot store. If we have a lower tail like this, then we'll have some deficiencies in wind generation, and that's probably cause power outage. So that's yeah, very nice, very useful clarification. So the lower tail will cause power generation deficiency, will cause blackout problem. That's more serious than the upper tail, which we just are wasting some energy, but it's not critical. So in terms of cost, this will, it's kind of a waste of energy, but there's no extra cost. But this one will cause some economic loss. So that's why no one chose this one, which I think is good. Okay, so now we have 3 choices here. So how many of you choose second one? Okay, 6. How many for the bottom left? Okay, 6. For the bottom right? 6. Okay, and we have about 30. No choices. Okay, so it's hard to choose. Yes. So apparently, most likely you don't have idea how to choose, and then we have equally probability to choose any one of them. So I probably understand now why you choose this one, because it looks nice, right? Just the curve really looks nice. I like this one because it's the normal curve. It's the Gaussian distribution, normal distribution. It's beautiful. It's really the reality. In reality, we have a lot of normal distribution stuff. That's why it's called normal. So this one is a typical actually curve that we observed, heavy tailed on both ends. So you can imagine the wind speed is not something so nice that we can model or follow really a normal distribution. It actually have a heavy tailed to the lower end and a heavy tailed to the upper end. This one is ideal for a wind size, this one. So averagely, they have the same wind generation, but very unlikely it will go below a certain value. So you can imagine a very stable wind generation from this side. No surprise, and it's very easy to operate. If you draw a curve at certain value like 10.5 for all 4 curves, for this one, you have the lowest chance to go below 10.5. So that's more easy to operate. Again, this is ideal, but this is what we observe in reality. So I will use this example to explain some issues in real applications, like people address the uncertainty, because they really care about the extreme events or exceedance probabilities, and they were assuming a normal distribution, and that's the problem. Okay, so for the 2 cases, now we can sort of define what we want for uncertainty quantification. To me, either quantifying uncertainties or uncertainty quantification is to replace the subjective notion, as we saw from the example. It's really subjective in different ways of describing the uncertainties. We don't want to be subjective. We want to use a rigorous mathematical measure for the uncertainty. And this information could be used to define the uncertainty. And the information including hard, we call hard or direct information, which is the information directly on the things we are interested in. That includes experimental observations or theoretical arguments from the literature or from database or from anywhere that has some relationship with what we are interested in. Or can be from expert opinions, because they know more really based on their experience. Or it can be soft or indirect information. Those information are the observations or arguments that are indirectly related. For example, we can use global sea surface temperature as the indirect information to infer or to get a better estimate of, I don't know, RCP or other physical input model parameters. So this is called soft information. So it's not direct on those attributes. Okay, some basic or even trivial probabilistic concepts. There are many different quantities that can be used to describe uncertainty. For example, the mean or confidence intervals, that's what we normally use. The mean is usually related to a bias or accuracy description, a confidence interval for precision. In reality, you want to be more accurate and precise. It could be a situation that we are accurate but not precise, or precise but inaccurate. I don't know how many of you have heard about these arguments, precision and accuracy. This is probably, I can explain it. Just use a few curves. In reality, maybe the true value is here, and we want to have a good handle on it. And what if you have some measurement and it has this kind of distribution compared to this kind of distribution, or so these are different situations. Even if we use probability density function to describe uncertainty, which is the way that I prefer, look at the 4 curves, 1, 2, 3, and 4. So you can imagine when we talk about precise but not accurate, we are talking about this one. That means we are very certain about this parameter, but actually it's wrong. So very precise but inaccurate. For the middle one, it has the widest distribution compared to the other 3. So it is the most imprecise. So it's not very not precise, but it's accurate. It's the only accurate one. So that's the accurate one, but not precise. That's for the second curve. But for the fourth curve, it's very precise, but inaccurate. In reality, you really want to avoid to reduce your uncertainty to such a level such that it is biased. Okay. So I have only one curve here. So this distance, the distance between the actual value and your mode or mean is the accuracy, and the bandwidth or the precision width is precision. All right, so we have other possible summary statistics in reality, in practice. You can use skewness curtices, like for the wind generation, wind speed case, or use median by sorting all your samples, or use mode, the most likely one, or percentiles. You can see what's the 1 percentile, what's the 99 percentile. That is used a lot in America. I don't know if used at other places to describe where you are. And the best way that you don't lose any information is the probability density and mass function. The density function is for continuous random variables. The mass function is for discrete random variables. Yet people can develop some other quantities from information theory, including the entropy. Entropy is after you have the distribution, either discrete one or a continuous one, you can use a summation of your probability times the log probability, or change the p to f for probability density function, f log f. Then for that case, you need to take integral instead of summation. Anyway, so entropy is one way to describe how much information you have for now. And even more, you can use relative entropy, also from the information theory, to represent the information gain. So say you originally have a distribution at the function q, and now after some updates, your new distribution become p. So this one describes how far from one probabilistic measure to another probabilistic measure in terms of PDFs. So this describes how much information changed from the previous status to the current status. We don't need to use this one, but later on I will talk about how to use information theory to derive a rigorous form, closed form of probability density functions. So that's why I'm talking about entropy. There are many other quantities defined by statisticians, but some have advantages, some has less disadvantages in terms of mathematical theory, but usually hard to explain in physical science, so let's not use them for now. Okay, so return to the example problem. Now we want to talk about, it's actually a UQ problem. It's not just describe the probability. Now let's do something fun. That probably will prepare you better if you want to play in a casino. So just a statement, well-quantified uncertainty will give you a reliable decision making. I think you probably will, you already know that, and you will agree more after you solve this problem. So our example is like this. So we have an input variable, or in physical science we call it parameter, input parameter, which is defined as the color of the block that the spinner will land on, just play it. It has uncertain outcome every time we play it. And the formula, which is our fault model, like the community atmospheric model, CAM, or other model. So this is the model. And here we have a model that if you bet €1, you get 0. That means you lose €1 on blue. You are flat on green, and you get $1 on red, and you get $3 on yellow. Not dollars, sorry, I'm from the United States. Okay, euros. So return, that's your model output. So global sea surface temperature or the future SST. That's your return in this model, in this case. So the total return after 60 plays. So what's the return? The approach, there are many ways. Like we discussed yesterday, we can look at different scenarios. Within each scenario, we can do some sampling, ensemble-based simulations. Or we can use the probability mass function to do a more systematic or exploratory sampling. So given the most likely estimate, so we did the exercise that the probability will land on blue is unlikely, right? But if in practice, you want to know what's the most likely outcome, that's the blue. So blue in this case is the most likely one, but still unlikely. That's the reality. So your most likely estimate is an unlikely estimate. So given your most likely estimate, you said, okay, I don't have the capability, or I don't want to spend too much energy to looking for all possibilities. Just look at the most likely one, which is blue. So if you are giving advice to your clients, so whether to go for it or not, the answer is no, don't do it. Because most likely you will lose money, $1 every time you play. So that's your conclusion based on your most likely estimate for the future. Perturbation-based scenarios. This is also another common way in science and engineering. So let's play with 3 scenarios. The most likely one, that's the base. But we also allow some perturbations, allow some other less likely situations, which is green and red. So let's play these three scenarios. And then your conclusion would be, given the 3 scenarios we are exploring, you will lose $1 and will get nothing, or you get $1. So basically, it's a waste of time playing this game. So your conclusion is, forget about it, don't bother, because really, if you just really want to go for fun, then do it. Otherwise, just don't bother. But the most reasonable solution would be based on probability mass function. You really want to need to explore all possibilities. And unfortunately, you cannot just even do 12 experiments to prove if you should go for it or not. But the PNNL-based approach will tell you, yes, go for it, unless something weird happened. For example, someone is playing a trick, like the spinner can never stop on yellow, or because of gravity effect, something like that. So we need adequate number of sampling, or a long enough time period of observation to prove many concepts in reality. If we have some data, like for the past 5 years, maybe we can add some different modules or calibrate a model to match the data for the 5 years. But if we want to use this model to predict the next 50 years, we are in trouble, because we are only matching the 5 years and we want to predict 50 years. You will see why. So we will play with this code in the afternoon if you want. We can use a code to simulate this system. So what's the return for the next 60 plays, or in climate science for the next 60 years? But you need to have a long enough story to really confirm that. So this is the the simulation results. We can pretend this is actually what will happen in when you are playing this game. So the first play, you get $1, then lose $1, then nothing, then lose, then flats, then lose, then win. So any pattern may occur. And if you do the accumulative return, so how much dollar up to this play, basically you add up all the numbers as a function of plays, then you start with a very losing pattern for the first 10 plays. So you may lose your belief in your model. Okay, so I think the model is wrong or something. Just you don't have enough observations. If you continue to play, you will see another different slope. By 60 plays, you will be getting $15. But then it becomes flat again. So again, in practice, some people use 2001 data, someone use 2001, 2005 data, someone use the last 5 year data. They come out to totally different models. They say, okay, this is my predictive model 1, predictive model 2, predictive model 3. And if you keep this model for predicting the next 50 years, it's losing $200, gaining $500, or flat. You don't get anything. You don't lose anything. So these are the divergence of different predictive models. They are training on different observations. Or you're training on Brazil, you're training in China, you're training in US, you're training globally. So you got totally different predictions. So if you have enough data, theoretically, you will have a pattern like this. With 120,000 plays, you will know your model is correct by assuming this probability density function for the 4 different outcomes. So the two messages, one is you need to observe adequate number of plays or time periods for validating your model. And you can update your probability mass function if you have such observations. That's what I'm talking about. If you put the board flat on the table, probably you are fine with equal probability on each block, such that the 4 numbers here, 5 out of 12, 3 out of 12 are correct. But in reality, it could be because of gravity effect, could be because the casino people is playing some trick. Then there are actually more chance to land on a certain direction. Then you need to modify your probability functions. Then you have a new model, or called an updated model with updated parameter probability functions. Then you will have a different curve. So basically, you can have the first 60,000 for training your parameters. That's what we call model calibration. You have a better model, then you can predict the remaining part very well. So that's the idea of characterizing uncertainties, update your information given indirect information, then improve your model prediction capability. Okay. So the UQ components, based on the examples, they are not quite representative of the practical problems, but it has most of the components. That may include reliable quantification of input uncertainty, including the parametric forcing, natural variability, etc. And you want to play with exploratory experimental design, efficient sampling, efficient ensemble sampling, to really understand what are all the possibilities. And then you have an accurate forward model. In our case, we have a really accurate model. Really nothing different will happen. And update our prior knowledge. So we have an uncertainty description. We want to update them, improve them, given observations, given some indirect observations. And then we want to quantify and reduce the output uncertainty. Not just, okay, we live with the prior knowledge, and we have a model. Let's say we want to improve it, reduce I don't call it reduce precision, to be more precise and be more accurate. We want to have a model in the middle. At the same time, we want to be as narrow as that. So very accurate prediction. So focus of this presentation, I was focusing on calibration. So as Charles termed it, so it's hydrodynamic, which I am not sure what does that mean. Anyway, so I will not focus on calibration anymore. I'll focus on how to derive probability density functions, how to derive your uncertainty measure. And then why we use efficient sampling, how efficient sampling can be used for our Ensemble experimental design. And then I'll talk about briefly about Bayesian inversion and Markov chain Monte Carlo simulation, and also some modifications like delayed rejection or adaptive metropolis, or some other design like a Kriging model for discrepancies, or refining your parameter set to have a reasonable region to develop emulators, something like that. So these are the solutions for some computational challenges of applying those calibration techniques. Okay, so very trivial, several trivial concepts in statistics. As I just mentioned, we have summary statistics. We can use the mean value, max value, the median or a mean, or quartiles. So what quartile means? How many of you never heard about quartiles? None of them? Okay. So if we have an ensemble of numbers, for example, so the first quartile and the third quartile means there are 50% of values are located within this range. The median is the one that is exactly in the middle. It's not the average value, it is the value in the middle. This probably is useful if you are writing a paper, this will add some fun stuff. What's the average value? Getting a hard problem for myself. 9, 10, 11, 12. Okay, that's the value we just played, 5 out of 12. No, 12 over 5. 2.4, right? So the average value is, so the mean is 2.4. That's the mean. What's the mode? The mode is the number that happens the most. So the mode is 3. The mean is 2.4. And the median is 3. So in this case, the median is the mode, and the mean is smaller than both of them. So this, you can see we cannot use like a mean or standard deviation to describe the bounds. It's similar to this example case. We have a median, which is the black horizontal line here. We have an upper quartile and a lower quartile. So the values between this range account for 50% of all the numbers. And we also, in statistics, we prefer this more, the whiskers, this bar and this bar. This bar is this quartile plus 1.5, the interquartile range. The interquartile range is from here to here. So this is just I want to explain what's in the box plots. I believe some of you have used the box plots to describe your data, or not? Anyway, so the message I want to deliver here is don't just always use the mean value or standard deviation. In this case, it's 11.3 and 1.0. Why it is problematic? Because if you use the mean plus minus 2.57 of standard deviation, you get a 99% confidence interval. So I reviewed many papers, they use this simple descriptive. So the mean plus minus 2.57 sigma, that's approximation of your 99 confidence interval, if it is normally distributed. And someone prefer 95% confidence interval, which is mean plus minus 1.96 standard deviation. So these two are problematic when you have data like this. Say you have an output of global sea surface temperature from Ensemble model predictions, 42 models, or from your own model, but with different scenarios. You have this kind of ensemble. Then don't use these numbers as your summary for all the different results. Instead, use the upper ones. Is a better choice. Justification is if you use 99 confidence interval for this case, it's 8.8 to 13.9. And if you really count the outputs in this range, it's actually 97.8% instead of 99%. Usually you're off by several percent. That's usually unacceptable if you claim 95% confidence interval. Okay, too much on this slide. Anyway. So these are some suggestions for you to use to evaluate or summarize your ensemble results. And the message here is, first, is it normal distribution? No, it's not normal. It's uniform distribution? Of course not. And most likely estimates, which is the mode. 3 for this case. And the mode for this one, I didn't plot it, is somewhere below this line. Perturbation-based scenarios. Some people use mean, someone use mode, someone use median. Choose any number, and then they play with bounds. For example, they use this value and this value. Or to be more complete, they want to use this value and this value. They can have a 3-level or 5-level evaluations, 5 scenarios, 3 scenarios. These are all not enough, because you really want to describe everything extremely, especially if you care about extreme events like extreme climate or flooding, in other places, earthquake, power outage. So you really care about these long tails. Use the 5 numbers, you really have no idea of what's going on in here. Okay, so we prefer the probability density function way to describe the data, either input or output. Okay, so, but how to start deriving the probability density function curves? Instead of playing with several individual levels or scenarios, how to sample effectively within a PDF? We need to have a PDF to fit, to sample with. But the issues are, the distribution can be truncated. For example, if you are playing with albedo, I don't know if it's a parameter or output.
It's an output, but you can imagine it's a parameter.
Okay, let's imagine it's a parameter. Thank you. Then probably it has a certain physical range. Maybe it's not a good example. Let's think about, let's say porosity. I don't know if you know porosity. Let's see how porous a sample is, like a sponge or soil. So the porosity can only be positive or can be 0. Let's see, so it cannot be negative. Okay, so the porous space cannot be negative. So you know the physical bounds, there's a hard limit of the lower bounds, which is 0. So that's the truncated distribution. So when you assume a distribution for porosity, there's a hard lower bound. Remember that. And in some cases, based on expert opinion, for certain parameters, they also set a lower bound and upper bounds. That's the case, you have both bounds, lower and upper bounds. Then we can have a bimodal distribution. That's very problematic, but it may occur in reality, or could be multimodal. So your data, after you take measurements of this data, it has this kind of distribution. Or it can be long tail distribution. So if this tail extends all the way to a certain range, which cannot be described by any standard probability functions. And then you could have, okay, these are all the very challenging cases that are listed. So we will have a truncated case, we have bimodal case, tail distributed case. Can we handle that? The answer is yes, we have some solutions. And then we have a situation, for example, the parameter may span several orders of magnitudes. I think in atmospheric science, there is some situation like this, right? Some parameters, they vary from 0.001 to 1,000. For this parameter, probably you don't want to use any uniform distribution because you won't have any samples near 0.001 in that case. For parameters spanning several orders of magnitude, usually a transformation, like a log transformation, logarithmic transformation is required. Okay, we can handle all these situations. Then, significant amount of zeros. For example, I'm living in our lab is located in a desert. So if we want to model the precipitation, so we have 300 zeros among, for any year, roughly. So if we want to fit the distribution for that, you will have a precipitation data zeros, and then high precipitation and low precipitation several days, and then 1 day, 2 days, 3 days, 5 days. The zero is for 300 days. How to fit this curve? These we all have some temporal solution, which I'll talk about later. How about last one? No observation, no measurement. So you don't have any measurement. You have no idea at all how to play with that. Yes, we have solutions. Oops. Okay. This is what I will be showing you this afternoon. We can play with the different packages in R to fit different type of distributions. So there are several packages, and you'll be seeing one of them this afternoon. You can fit any type of distribution given your measurements. For example, normal, log normal, Poisson, exponential, gamma, beta, uniform, etc. For tail distribution, if we have time, we can play with these packages. For bimodal distribution, for truncated distributions, we have some solutions. This is an example of how we fit, if we have measurements, say 20 or 30 measurements of certain parameters. We want to know what's the distribution. We can fit a distribution. We can do a statistical test. Usually we do a normal test and plot QQ plots, quantile against quantile plots. And to confirm it is this kind of distribution, the probability density function and the cumulative density function match the theoretical one. So if you want to explore more, we'll talk about that. But that's the statistical theory. Which is the this is not the wind speed data set anymore. QQ plot means quantile against quantile plots. Okay, should I explain? Okay, what time? Okay, so let me see. We have about 30 minutes. I'll just roughly explain what's going on here. If you have a sample set, say 20 numbers, you want to know if it's normal distribution or not, then you can have a theoretical relations which has 20 numbers generated from normal distribution. Then you sort, you know sorting, right? You sort the both data sets, the exactly normally distributed and the one you assume or you speculate is normally distributed. You sort both data, and then you do one-on-one match and plot the scatter here. And it should follow a straight line. If your sample follow normal distribution, you should observe a straight line here. If the two distributions are different, then you will see deviations away from the straight line. QQ plots is a basic technique. Not very basic. It's a fundamental. How to use that word? It's the technique we use. Instead of we use the p10, p-value to describe, this one is more sort of straightforward. It's a more well accepted. To plot quantiles of your sample against quantiles of a theoretical sample, you want to have a straight line to verify it is normal distribution. If it's not, you are not in trouble. Try another distribution and try to see which model fits you best. So this is a model selection. So the distribution usually have a similar number of parameters. So the one fits your sample better is the choice you can go with. And you can email me, if we have the link. So if you have questions about the fitting and about this concept, and I'm willing to help you, you can email me about it. Okay, so in the afternoon, you will see you will really have the power to fix any data that you will be encountered in your practical problems. But what if you don't have any measurements, but you do have some experts' opinion on some parameters, like what's that, RCP, the expert says, or the experts say, the bound is between 2.5 and 8.5, if I'm correct. That's your information. And you may say, I don't have any assumption, or I just assume uniform. Actually, we have a base here, which is this theory, information theory. So given statistical knowledge from the literature, from other people, papers, articles, or from a database, or from experience, you can always derive a closed form. Closed form means we use number to describe the curve. Can be derived using minimum relative entropy theory. It's not just my development. It's including a huge group of people. They developed a lot of, they have a lot of nice work on using the relative entropy theory to define probability density function. So this is the formula that I'm showing you. This one is called the truncated normal distribution. This one is called the truncated exponential distribution. So you can forget about the mathematical stuff for now. I just want to let you know that we have the flexibility of obtaining any shape of distributions, truncated in a normal curve, but truncated, or in a uniform form, of course truncated. It cannot go from the negative infinity to infinity, or a truncated exponential curve. So any shape of PDFs can be derived given this formula. This one can expand every time it goes. If you have only the lower bound and upper bounds, then you take the limit of beta approximately to 0. If you have a lower bounds and upper bounds, that formula will give you a uniform distribution with the probability f(x) is equal to 1 over upper bounds minus lower bound. So now you see you already have a base. So if someone tell you for this parameter the lower bound is 5, upper bound is 10, then you say it is uniform distribution. It's not because I'm just assuming it, or I just want to take this choice. You have a information theory to confirm that it is uniform. But if you speculate the mean value is here, or for the RCP case, you assume the mean value is somewhere towards the upper bound, because you know from many studies the scenarios near upper bounds is a little more likely. Mean value could be here, then it is not uniform anymore. It should be a distribution like this, or the other way actually. So this is your distribution. In an example here, the mean value is closer to the lower bounds. Then you have a distribution truncated exponential like this. If you have a variance also, based on some data from other sites, you know the variance is also informative. The variance is not smaller than, say, a quarter of this range, then the variance also matters. You have a lower bound here, upper bound here, and you have a variance. Then your distribution could be like this. This is your mean value, lower bound, upper bound, mean value, and with some standard deviation information. So you can have all kinds of combined information. Then you can always apply this formula. Question?
Okay. These are all based on the statistics, right?
Yes, purely based on statistics, no other information.
Yeah.
So you don't have any data to play with.
So there are other methods that criticize the statistics, like for example the info gap theory. So I think they have not been applied in climate science.
Gap theory.
Info gap, yeah.
The
info gap theory. So it's significantly criticized the statistics, and it's not based on what we have learned about statistics. And it's about uncertainty quantification.
Okay, it's good to you can send me that. So my belief is we need to have a base. We need to have somewhere to start with. If they criticize these statistics, it's fine. So I'm always not against any alternative concepts. Just as long as they have a strict way or rigorous way to derive the prior PDFs to start with, not from any speculation. So it's just from my mind, I just want to use this or that. So that should be more criticized. That's my idea. Okay. Okay, so after we quantify uncertainty, we can do a systematic ensemble design using efficient sampling, not arbitrary sampling compared to arbitrary sampling. The application is after we sample the uncertainty from this distribution, we can do a more reliable sensitivity analysis, not a perturbation based or not based on some arbitrary samples. And we can do parameter ranking and screening, see which parameters are important or not, and reduce the parameter dimensionality based on the previous studies, or develop predictive models to link the outputs, model outputs like CAM outputs or CMIP5 output to your input parameters, or scenarios even. You can develop function between linking them. Or develop surrogates, which is similar to this, but surrogates can be used further for model calibration. For example, you cannot afford to use the model directly because it's too computationally expensive. They can use the surrogates as an alternative. For this case, you need to validate your model to make sure the surrogate actually works, or you can develop surrogate at a certain location or certain period. It is not always true. So if you prove the surrogate simply doesn't work because of the complexity of your combined model, then don't do a surrogate-based calibration. Then sampling the posterior. Sampling the posterior is actually the calibration. So basically, you want to get to your posterior with observational data. So this we have talked about just now, what's calibration, and we will be talking about that very soon. So ensemble design, the sampling approaches. After we have a PDF or a PMF like this, how to make sure we have enough representative samples or ensembles given a PDF like that. The very basic or naive design is the grid design. I think Dr. Duan talked about this on Monday afternoon. If we have only 2 parameters to play with, then grid design is very nice. Or if you have a one-dimensional problem, it's also very nice. You can really cover the space with this like 260 points. You can have 16 levels for each dimension. But what if you have 3 parameters? Then 16 to the power of 3. That's several thousand. Then if you have 10 parameters, then 16 to the power of 10. That's 1 billion or 1 trillion. So you want to evaluate 1 trillion ensemble runs? That's not possible. Let's just forget about grid design, which is a very bad approach. And grid design versus Latin hypercube design. This is, I have a similar idea. I have 2 plots showing this and this, but I found this guy plotted them together, which is really nice. I borrowed the figure from this guy, Urban 2010 paper. So they have 4 parameters. Let's pretend this is RCP scenario parameter. This is another factor, can only take discrete levels, or these 2 are physical parameters that can be continuous random variables. So Latin hypercube sampling is, how many samples are here? 81. So if we plot the paired scatters between any 2 pairs, you see, between any 2 parameters, we can have a scatter. So this is how we display multi-dimensional data. I don't know if you used this technique or plot before. So this is how we display the different combinations of all these different type of parameters, maybe. So with 81 samples, or 81 ensemble of 81 members, for the grid design, we can only have 3 levels for each parameter. But for Latin hypercube design, we can have 81 levels for each parameter. For RCP case, if you play with 42 models, maybe the 42 have 8 or 7 or 42 scenarios, say. But with this 81 ensemble, you can have 81 RCP levels. And at the same time, you can have 81 levels for each of other parameters, which is the nice thing. Actually, someone may argue that's what I heard, Markov chain, Monte Carlo, simply Monte Carlo. So that's simply Monte Carlo approach. Yes, you're right. But can we improve the Monte Carlo approach by using a nicer design, including Latin hypercube and Concy Monte Carlo? Many works proved those two can be several times or hundreds of times more efficient than regular Monte Carlo sampling. So because they will make sure if you divide the probability space into pixels, each pixel will get a sample. That's guaranteed. Of course, Monte Carlo is another idea, is to design a matrix array of points such that a space can be completely filled without gaps and clumps. That means no two points are too close to each other and no significant gaps like what we observe here. So Monte Carlo sampling can also guarantee, pretend there are 81 points. You can have 81 levels for P1, 81 levels for P2. The problem is we have gaps. We want to know what's going on here. Maybe that's the critical region. But in the other two cases, really, they can fill in the whole space. So no exceptions or no surprises. That's the idea. So I'm plotting the spatial coverage by the three techniques given 32 samples only. Use only 32 samples, we can cover the whole space using the other two, but we'll have gaps for Monte Carlo. So if you have a chance to use the Monte Carlo approach, don't use it instead of using the other two alternatives. Like for 256 samples in an ensemble, you can really completely fill in a region. This is just a two-dimensional display, but for all other dimensions, the spaces are also very well filled. So that's the nice thing about these two approaches. So LHS, Latin hypercube sampling, and QMC can be used to design your ensemble experiments. I added this after the discussion yesterday. But not this one. Hierarchical parameters. What's hierarchical? Hierarchical means the parameters don't have to be parallel to each other. You have albedo, you have, I don't know, average wind speed. These physical parameters, they are parallel to me. And you have some hyperparameters that can describe these parameters, or they are factors like your scenarios. So you have 10 scenarios. For each scenario, you were planning sample all other parameters given each of a scenario. Actually, you can also sample the scenario at the same time. So that's what I call the hierarchical parameters. You don't need really more samples by adding scenarios in the sampling design. And it also can be mixed types. Like for many medical experiment, we want to know if a medicine is effective or not. We can have a high dose, medium dose, and low dose, 3 levels. So these are the typical design. So those parameters are discrete or categorical parameters. Or they can be physical, continuous. That means the wind speed or other physical parameters, they can take any values in their reasonable range. Can be normally distributed, can be uniformly distributed, different distribution types. Or it can be independent or correlated. Someone argued among the 20 parameters I'm playing with, P3, P5, P6, they are correlated. Then we can apply Trieste compensation onto these subset parameters to make sure these 3 will follow the appropriate multivariate Gaussian distribution. So mixed data types, mixed parameter types, mixed distribution types, and with or without correlation, or with hierarchical parameters, we can all apply the efficient sampling for your ensemble design. This is one example of UQ application. for a land surface modeling study. It doesn't have all the components, but some of them. And we start with a set of parameters. For each parameter, we collect all the information that we can have, and then derive the probability density functions, and then generate samples using quantum Monte Carlo sampling to fully explore all the possibilities in the parameter space. And then we generate ensemble parameter sets and run ensemble runs using CLM forward model, the direct model. This we can apply the parallel computing. We run all the cases simultaneously on the supercomputer. So several hundred cases at the same time. So in a few days, we get all the results. And then we can analyze the output responses, like latent heat fluxes, or sensible heat fluxes, or runoff. And then look at the output statistics. We also fit probability functions for all these outputs to understand what are the different uncertainties. Is normally distributed or not? What's the exceedance probability? It's more related to heat extremes or floods. And then we can go further by developing surrogates based on the ensemble runs and to do the model reduction via calibration, so surrogate-based calibration. And we did try the calibration using the CLM model directly. So there are different considerations which I will talk about later. So these are the probability density functions given our prior knowledge about all the parameters. They can take all kinds of shapes. And we will try to fill in, as I just mentioned, we want to fill in the probability space. So any possibilities will be explored. But in the parameter space, the actual physical parameter space, it may look like this. For example, for the second parameter, it is uniform. And for the sixth parameter, it's also uniform. So between P2 and P6, we should be able to see P2 and P6. So this is the scatter between P2 and P6. So it's uniformly distributed in the probability space and in parameter space. But some parameter may have a better chance to take a smaller, lower value than the median. Like this one has a higher likelihood towards the lower end, P1. That's what we expect. So P1 has more samples near the lower bounds, but fewer near the upper bounds. That's after we convert the samples to the parameter space, we should have a scatter like this. So this is our ensemble design. For each point, it is a unique combination of parameters. We run all these ensemble runs. We can look at outputs. The outputs, model outputs, latent heat flux, or sensible heat flux, or runoff. We can plot at different months what's the range from the ensemble runs. So this gives us a wide range. That means, given our lack of knowledge of the parameters, we may expect totally different simulation results. If we want to do a model comparison, we cannot just pick any one of them to do a comparison with others. We want to use our best capability. So that's justifies why we want to go further to really narrow down the bounds, the probability bounds for the outputs. How to do that? We can look at the sensitivity of the parameters and identify which parameters are more identifiable by looking at the observability. So I don't want to get into details anymore because we have only 10 minutes left. So it's based on, for each parameter, we know how much of variability in the outputs can be explained by that parameter. The more it explained, the more observable of that parameter. And differentiability means sometimes parameter 1 and parameter 2, they interact with each other. They play with each other together to explain some of the output variability. Then it's hard to differentiate them. So this is the formula of how, by removing and adding back the fitted sum square. This is probably too technical. Just I want you to understand we have some criteria to tell if a parameter is important and if is a parameter, then can we differentiate or can we identify it from the observations? So based on these studies, we can, based on the parameter sensitivity patterns, we can classify the complex climate system into maybe simpler systems. For example, across the United States, we want to do model calibration at each watershed. These different small areas are the individual watersheds in the United States. So we cannot do the work, like calibrate at each site. That takes probably 30 years to do that. So how about we classify them and see if we can reduce the computational effort in the calibration, which we proved is possible. By looking at the parameter sensitivity or identifiability pattern, we saw different regions have different parameter sensitivity patterns, and each region is dominated by only 2 or 3 or 4 parameters. So we can only look at the reduced number of parameters instead of the complete parameter set. So reduced parameter dimensionality will enable calibration because it's ill-posed. This term I want you to have in mind is called ill-posed problem. When you have a model, you have the capability to make it better by calibration. You want to know beforehand if your problem is ill-posed or not. 5th time. All right, try to avoid it. Ill-posed problem. This is another critique by on statisticians because many problems are ill-posed, such that really very fancy techniques cannot be applied in practice. A simple example, I always use this one. If you have a problem, a plus b is equal to 5, and b plus c is equal to 3. Tell me what's a, what's b, and what's c. Can you solve it? This is a similar idea as the ill-posed problem because you really have more unknowns than what you have, the information you have. ABC can be anything. So then you need some constraints on A. So A is between -1 and 1. This is your knowledge. Then it's starting to get less ill-posed because you know more about A. Then you have some idea of possibly what's B and C, but they are in a sort of a uniform distribution or some other. What about if I tell you B is between 0 and 0.1 and A is belong to -1 and 1? You can play with this problem. I believe you will have a very nice information about C given that situation. So we have some equations, that's forward models. And we have some constraints. Now you can feel comfortable about C because C is constrained given A and B are constraints. So this is a less ill-posed problem, but still no unique solution, right? You still don't know exactly what's A, B, and C, but you know where C is, the range.
But there's no solution for A plus B equals 5 because B is between 0.
Right, no solution yet, but you now have a range for C.
But it's still
that,
a post problem because the
yeah.
first equation.
Yeah, we call it still pose problem. So this is the uncertainty quantification. So now we have an uncertainty about C. C is not a unique number that satisfies this equation, but C has a range given A and B. Or
but there's no 2 possible combinations that A and B would equal 5.
oh, that's what it said. Okay, thank you. That's a very nice observation. Okay, let's make it more reasonable. See, there could be unreasonable constraints or wrong constraints in practice. I like that. Okay, so I don't know if this one is more reasonable.
Yes.
Yes.
Okay, so now C has a range. Let's make it even more. From 1 to 1.1. This one from 1 to 1.1. So you're almost exactly sure where is C.
Still the same.
Sure. So if the P, yeah, that's not possible. Okay, let's don't pose constraint on B then. Okay, so now the question is, what's the distribution for B? Now B is now it's okay. You can try it. You can do it by hand or computer. See if you can have a bound. If you cannot find a location, or you found that B doesn't exist, that's the problem with ill constraints, ill posed constraints. Okay. So constraints usually are soft and not very informative. If it is very informative, it could be for in a situation like precise but inaccurate. Anyway, I'll skip this one. Too many equations. That's the one I developed with the entropy theory to get posterior distribution. But we have only 5 minutes. So metropolis histine MH sampling. Several of our speakers have talked about that. I'll skip that also. And a few modifications on that. There could be some delayed rejection. This basically want to increase the acceptance ratio of the sampling of the sampling point. And adaptive metropolis is to introduce modification of your proposal distribution given the previous samples. So those are the updated versions of the DRAM version for Markov-chain Monte Carlo sampling. This is an example that you will be playing with in the afternoon. You can get probability density function, the posterior distribution function for 4 parameters given a particular forward model. In practice, you can replace your forward model with your own equation. If you have a climate model, you need to replace with your climate model. If you have a equation to object function to minimize, you can use that code to minimize, to find the best solution of your parameter values. We apply this approach to different flux tower sites and watersheds in United States, and this is what we obtain. This message I want to. A question? Okay. So look at these 3 parameters. We have a black line here, and a black line here, and a black line here. These are the parameter values hard-coded in the community land model. So basically, the whole United States assume these values are the correct ones, and we have no idea if it's good or not. And after we do the calibration, we see, okay, you are not off by assuming this value, but the true value maybe is more close to the red line here. And for this parameter, you're way off. That's what we found. It's actually the cause of the systematic underestimate or bias, or we thought it was model structure errors. But in fact, it's probably caused by the parameter. I will prove that. Why we need to do calibration to guess the best, the most out of our model, then do the comparison with others. So this is a wavelet analysis. I don't know if you have ever used wavelet analysis. I will use wavelet analysis to look at the ensemble simulation errors, see how the errors are distributed. So which temporal scale are the part where we have the largest errors, for example. I applied the technique to all different MOPAC, the watersheds, and on the ensemble runs, just to see the distribution of the errors at different temporal scales. So see, this is the time frequency analysis at different spatial and temporal locations, sort of. So really we can understand if there are errors and how large and where and when. So different locations have different distribution of these errors. In the northern states, there could be ice melting module is not capturing the nature very well. In Florida, maybe it's not capturing the wetland process very well. That's the potential idea or guidance on looking for model structural errors. So after we do the calibration, see what's the difference. before calibration, before we improve the parameter values, we have this kind of range of errors at different scales. After we do the calibration, the errors at 10-year scale and the yearly scale disappears, basically. But there still existing some errors at the daily and monthly scale. So those errors are sort of, as Charles or defined as irreducible. For the irreducible errors, potentially they are the monostructural error, or potentially it could be a minor observation error. So we don't know yet. But that's the message I want to deliver here is we need to calibrate our individual models to reduce the parametric error uncertainty first. Then the remaining one could be monostructural error. If it is irreducible, that's fine. So this error and the corresponding misfit should be used to derive the likelihood of this model and to be integrated with other models for an ensemble prediction. Okay, I don't want to do it. That was my summary over that analysis. And other implementations, in reality, if you find it's simply impossible to use a markup chain in Monte Carlo because it requires thousands of runs, you can think about the surrogate-based inversion. For that one, you need to validate your model. You have a training data set and train your surrogate model and use your testing period to see if that model actually works. If it works, do it. If not, just forget about it because your system is too complex, I guess. And you can filter the parameter set. You have an ensemble parameter set. Of course, there are many challenges as you just explained. The sampling could still be arbitrary, someone argues, because even if it is from information theory, it is somewhat doesn't really exist. That's also the challenge on Bayesian against the frequentist. Anyway, there could be a physically unreasonable parameter set that has been generated. We can filter that out by adding a classifier, or we can add some terms. This is a similar idea as to add a term, I don't know, called epsilon or gamma in the slides that Chris showed before. Not Chris, Charles showed before. The extra monostructural errors. So we can add a creation model. So we'll talk about that if you are interested in it. Or we can have correlated errors. So this is another way to define, I don't know if people agree on monostructural errors, is the errors should be correlated. If you have a large error at this location, then you are expecting to have a large error right next to each other at adjacent time steps or locations. So those errors are correlated. So you don't want to overweight, you don't want to assign, you don't want to double counting the effect of this error. Then you can assume a correlated error by assuming a spatial temporal correlation parameter to describe such error. So this is another implementation we have done. The last one is what I want to also draw your attention is the scalable adaptive chain ensemble sampling, which is the ongoing project which we are working on with the Sandia National Lab. This software we call such as a scalable adaptive chain ensemble sampling. This is the approach to handle expensive models with the parallel computing capabilities. Okay, so 5 minutes past any time. So two softwares which are unique compared to the standard UQ packages, uncertain quantification packages. That you're including sampling, including surrogate development, including sensitivity analysis packages, or surrogate-based calibration. But the two unique parts in our approach, one is the prior PDF derivation and a sampling software, the coupled one called MRE QMC, and another one such as, which are to be released next year. But if you need any help using these techniques, we can collaborate, for example. Okay, a summary. Parameter dimensionality can be reduced based on parameter screening. to make your problem less ill-posed or to have a better understanding of the relationships between your model outputs and the input parameters, but that rely on your exploratory or effective ensemble design. And complex systems can be classified into simpler ones by analyzing your results so that you understand that at different regions, maybe they behave differently. And at each region, you may have your own dominant parameters to play with. And reduced dimensionality will make the problem less ill-posed and make your solution more narrowly bounded or with reduced uncertainty. And the scalable ensemble sampling is one idea. To go with expensive climate models, instead of surrogates, you can use the climate model directly, but you cannot afford a lot of numerical simulations. Okay, so these are these kind of topics we can continue this afternoon. At least these things, just the problems you may encounter in your actual applications. So we'll talk about that around 4 o'clock for 30 minutes on this. Okay, that's it for the talk. Thank you.
Any questions? About sampling?
So yeah, in the lab we can talk about more of sampling in the discussion. Okay, it sounds like I don't want to answer questions.
So then, Chris.
The quasi-Monte Carlo one, I hadn't heard of that one before. Then I looked it up, it was using random numbers.
Mm-hmm.
So could you explain the quasi-Monte Carlo sampling?
Okay. Sorry. See, okay, so probably a two-dimensional example is visualize this, looks better. So we have parameter 1 and parameter 2. Assume P1 and P2 follow a uniform distribution between 0 and 1 and 0 and 1 for P2 also. So you want to fully explore all possibilities of P1 combined with P2. Someone say, my model is expensive, I just play with this one. The 0.5 and 0.5, that's the very likely one, most likely one. Someone say, I want to be more thorough. I want to play with 3 levels of P1 and 3 levels of P2. Then you have 9 combinations. And the problem is, for each parameter, you still have only 3 levels. So you only know what happens very extremely low, extremely high, or somewhere in the middle. What's going on in the middle? You don't know. Your response, your model response could be very likely it's like this. It has a minimum in this region, which you will never have the chance to explore. You don't have a sample here. So Monte Carlo sampling has the idea of instead of fix these locations, allow some randomness of these points. So you still have 9 points. They are scattered randomly here. So what's the good thing about it is if you project of each point onto the P1 axis, you have 9 levels. So you're looking at 9 levels of P1. And if you project 9 points to the other axis, you also have 9. So you are exploring 9 levels of P1 and 9 levels of P2 with only 9 points. That's the better thing of the Monte Carlo. But the Monte Carlo has a problem of having a gap here. You still have the chance that the minimum is in this region and you didn't have a chance to explore. So the better way is letting half-cube sampling or quasi-Monte Carlo sampling. Letting half something still allow some randomness. The idea is you divide your space into many blocks and make sure each row and each column, in this case we divide into 9 rows and 9 columns. We make sure each row and each column has a sample. So that means if you project the samples down, you'll have 9 levels for P1, 9 levels for P2, and they are relatively evenly spread. So you cover the full space and make sure each row and each column got samples. And the nice thing is each row and each column got samples. The bad thing is still could be a gap. Because if this row got sample here already, and this row got sample here already, this row and column combined won't get any sample. So there still could be gaps. Theoretically, if you have enough samples, I don't want to say you need the same amount of samples like the Monte Carlo. Monte Carlo, you may need 5,000 to cover. This one only needs 100 to cover it. So an alternative is called Monte Carlo, as just Chris was asking. So Monte Carlo is, not forget about the dividing of the domain first. We just design an array in a certain pattern way in 10, 20, 30 dimensions. It can go up all to 30 dimensions, for example. If we have a 2-dimensional, you design an array like this. If you have a 3-dimensional, into the board, the other dimension, you shift these points in and out the board, also in a certain array. So this is really a deterministic way to determine these points, just to fill in the space. So it's a technique to fill in the space with a predefined array. So it works in a comparable capability as Latin typical sampling. So it's a design of the points to fill in the space.
I have 2 questions. In the derivation of the probability density function, in the case where you have no observation data, how do you deal with a case? How do you deal with the case where your distribution does not fall with any of it's not in among any of the known distributions like a uniform distribution?
Right. So good question. I will answer this first, and then you can ask another. So the question is, if the distribution type doesn't follow any, which is we usually don't draw that conclusion. So it always fits one of them better. So that's one solution. Find the one theoretical distribution that best fits your data. So we don't have exactly fitting. There's no such thing called the perfect fit, right? So among all the distributions, pick the one that fits your data the best. That's what I explained in the lecture. So that's one solution, found the best fitting. Then if you are talking about the distribution doesn't fit the theoretical one, like the 10 in the list, usually that's tail distribution, or a multi-mode distribution, or what's the other one that I talked about? So if the weird pattern like this happens, we still have solution as I mentioned in the lecture notes. So check the lecture notes, see if there's any other weird things you can see beyond that. Then I will try to find a solution for you. But I thought I sort of covered all the possible patterns. The data could be, okay, so your histogram, maybe you draw a histogram, it could be like something like this. You said, okay, it sounds like it doesn't fit any distribution. Actually, this could be some outliers. A uniform distribution will work. So if you see multiple peaks, it's very likely you don't have a reasonable number of bins. If you group these 3 together, and these 3 together, and these 3 together, you see, so visualization is a tricky stuff to change your mind probably. So histogram is probably not a good idea to fit to give you an idea of what distribution it is. It may have multiple peaks. If you have only 10 points and you have 5 peaks, then we'll talk about that. Usually 10 points are not enough for you to fit any PDF. We don't have enough information to fit. What's your second question?
The second question was just for you to tell us the meaning of some of the variables you use in your formula, which you use f of x was equal to the formula you gave
P.
in one of the slides to derive the derivation, the probability density function. It was very complex, but you didn't give the meaning of those variables. Some of those variables, I wanted to know what they stood for.
The complex formula of deriving PDFs given statistical moments.
Yes.
So these are the fitting coefficients. So when you have constraints like the mean, the bounds, the moments, m as the mean, sigma as the deviation, lower bounds LB, upper bounds RB, and then the beta and gamma are coefficients, which is from the code, which the solution is solved from my own code, which has not been released for probably next year. But if you want to have your closed form, I can derive the formula for you. Just provide you the coefficient, the beta and gamma. So they are not in a standard distribution. They are truncated normal distribution. And why we really be careful, but someone may argue it's really trivial. This one,
Jason, maybe you can answer the question more quickly, because I think we should probably start.
Yes. Okay. So yeah, the quick answer is yeah, I can solve that. Provide the beta and gamma to you. Provide the values to you for your particular data set. And okay, we'll talk more about why we deal with the truncation.
So let's start at you, if you say quarter after.